video will be about families of functions. Now, the description families of functions can apply to a lot of graphs. You can use it on any graph, actually. But specifically, we're going to be applying it to absolute value graphs. The equation of a basic absolute value function looks like this: y equals absolute value x. And the basic graph starts in the center and ends up making a V shape. And specifically, it's going up 1 over 1, up 1 over 1. Same thing to the left, up 1, left 1, up 1, left 1. Makes that V shape. This is our basic absolute value graph. When you change the equation, it's going to change the graph. So if we change our basic absolute value function and we add or subtract a number inside or add or subtract a number outside, it's going to change where this graph is. So inside is called a horizontal shift. And it's opposite of what we expect. When your number inside is positive, that means move to the left. We would think to the right because to the right is our positive numbers, but anytime you're in absolute value bars or for quadratics, you would be in parentheses. Move the opposite of what you expect, which means negative will move to the right. K outside is our vertical shift. This will move our graph up or down. And it's exactly what you expect. Positive will move the graph up. Negative will move the graph down. So let's see an example of this. Let's say we have y equals absolute value of x plus 2. So our basic graph was that graph that was exactly in the middle. And our plus 2, it is inside the absolute value bars. So according to what we had written up above, that means this is a horizontal shift. And specifically, it means a shift to the left. So shift left 2. That means this picture of the V, the entire thing is going to move left 2 spaces. That's our new graph. Sometimes you see just the ending result. Sometimes they shift it and leave the beginning. That was our basic absolute value. If we move it left 2, that's our new graph. We can do this with a vertical shift as well. So our basic absolute value starts in the center. Minusing 3 outside means to shift down 3. So we would take the graph. I can actually slide it. You would have to just count down 3 and redraw it. Slide it down. That's our new graph. So we can shift left or right. We can shift up or down. We can do both those shifts together. What if we had y equals absolute value of x minus 1, actually let's do plus 1 minus 2. Now we have 2 movements. Inside is our horizontal shift. Positive says move left 1. Outside is negative. That means move down 2. So our basic absolute value function, from there, this time instead of sliding it, I'm going to just count. From there, I would move left 1, down 1, 2. And that would be our new graph. And again, specifically, it's going up 1 over 1, up 1 over 1. Did not draw my picture super accurately, but I probably should. It's going specifically up 1 over 1. The left side's fine. So now that we know these movements, we can also be given a graph and need to write an equation for it. So since it's this V shape, we know its absolute value. We know it has a y and an x, and then it possibly has an h to fill in and a k to fill in. So I really just focus on that point, the vertex of the V, and I say, well, how far did that move from the center? So if I were to start at the center, I would have to go right and then up, and specifically I'd have to go right 1, 2, 3 spaces, up 1. So I went right 3. This was opposite of what we expect. Right actually means a negative 3. Up 1 means plus 1, and there's our equation. Now, there's more to it than just this. You can do more than just shifts. You can also do a stretch and a shrink, or a reflection. So with a reflection is when you put a negative in front of the absolute value bars. And this could be any, negative 2, negative 1/2. All of those would still reflect. When we reflect the absolute value graph, we take our original graph and we flip it upside down. So reflection is across the x-axis because we're flipping it upside down. So if we were to flip this upside down, our new graph would be the green graph. That would give us a reflection. When you do reflect and you have multiple things going on at once, we usually wait till the end to reflect. So anytime you're doing shifts and stretches, shrinks, or reflections, you shift first and then worry about your stretch, shrink, and reflection. So along with reflections, we have stretches and shrinks. That happens when you have a number in front of the absolute value bars. Usually we represent it as A. So usually we take this and write it as y equals A, absolute value x. So that A number in front will tell us, hey, we have a stretch or shrink, but we need to know which one is which. So the A in front, if the absolute value of A is bigger than 1. And we say absolute value because this can apply to both positives and negatives. So if this were 2, absolute value of x, you'd have absolute value of 2. Absolute value of 2 is still positive 2, which is bigger than 1. But it could apply to the negative 2. If A was negative 2, absolute value of negative 2 changes to positive 2, so it's still bigger than 1. So it's all numbers bigger than 1 and all numbers smaller than negative 1. That means it's a stretch. And when you stretch it, it is going to move closer to the y-axis. This is what a stretch looks like. We went from purple to blue, and it brought us in closer to the y-axis. A shrink is when that number in front, A, is less than 1. And again, absolute value. So these are fractions. Numbers smaller than 1 can be 1/2, 1/3, or decimals, 0.75. But they're only fractions smaller than 1. If you had 5 halves, if you divide that out, that's 2.5. That's bigger than 1. So numbers smaller than 1, but bigger than -1. Again, that absolute value involves the negative, so negative 0.5, when you took absolute value, would still be smaller than 1. So a shrink is when the absolute value of that front number is smaller than 1, and it is going to go further away from the y-axis. From that purple, now we're going away. Shrink. Or you can think of it as getting closer to the x-axis. So let's do an example. I equals -3 absolute value of x. So we don't have any horizontal or vertical shifts. We're going to do a problem where we do it all together, but for now we're just looking at the number in front. So that means we still start in the center. It's still going to make a V shape, but I don't want to draw the rest of the V until I know what's going on with my number in front. So -3, we want to absolute value it. That makes it +3, and decide, is it bigger than 1 or smaller than 1? Well, 3 is bigger than 1, which means this is a stretch. Second, negative means it will flip upside down. So now we're actually going to be going this direction. So the way we figure out where our next points will be, if it's the basic one, we'd followed that pattern of up 1 over 1, or reflecting would be down 1 over 1. We're going to use this as a kind of slope to help us find the new pattern. Every slope has to be a fraction, so I'm going to put -3 over 1. That would mean we go down 3 spaces because it's a -3 to the right one. Down 3 spaces to the right one. But because this is absolute value, we know it's a V shape, so we have to repeat it on the other side. Down 3 spaces, left 1. Down 3 spaces, down 3 spaces from this point, left 1. And I could keep going and draw as many points as will fit on my graph. So let's see an example with a fraction instead. So our fraction is 3 over 4. We look at the number in front. Absolute value of 3 over 4 is still 3 over 4. Then we have to decide, is this bigger or smaller than 1? If you're not sure, make it a decimal. 3 divided by 4 is 0.75. That is smaller than 1. So that means this is a shrink. Again, we have no horizontal or vertical shifts, so we start in the center. And then this is already a fraction, so we can use that as our pattern to follow. It's similar to slope. It's not exactly a slope, but similar enough that we can follow that same kind of pattern. That means we go up 1, 2, 3 over 1, 2, 3, 4. Up 1, 2, 3 over 1, 2, 3, 4. But we know since this is absolute value, we have these bars here, meaning absolute value, that we have to repeat this. Up 1, 2, 3, left 1, 2, 3, 4. Up 1, 2, 3, left 1, 2, 3, 4. And that gives us our graph. So let's do one where we combine horizontal, vertical shift, and our stretches, shrinks, and reflections. It's going to have everything together. That equals -1/2 absolute value of x plus 1 minus 3. So when we're doing this, we want to do horizontal and vertical shift first. Horizontal shift is left 1. Positive actually goes to the left. Vertical shift would be down 3. We have a negative in front, which means we do reflect. Absolute value of this front number is just 1/2, which is smaller than 1, which means we shrink. So now we've identified everything we need to draw our graph. So starting from the center, we're going to do our vertical and horizontal shifts first. So from the center, we go left 1, down 3. Left 1, down 3. This point will be the V on the vertex. We know we're reflecting, so we know we've got to go down from there. We know it's a shrink of 1/2, so that's the pattern we follow. Down 1, right 2. So down 1, right 2. Down 1, right 1, 2. We have to go the other side. Down 1, left 2. Down 1, left 2. And that would give us our graph. They may ask us again to write an equation from a picture. So we do our horizontal and vertical shifts first, just like we did when we were graphing it ourselves. From the center, we had to count right 1, 2, and down 1. So when we're filling in our equation, we know we have an x. We have right 2. That means -2, opposite of what we expect. Down 1, exactly what we expect when it's vertical, so negative. Then we have to decide the number in front. We are flipped upside down, so we know it's negative. And then from that starting point, I need another point. So I'm going to look for it to cross exactly, like right here. Crosses exactly at one of these crosshairs that were gray from the graph. And then I can count myself. So following the pattern, I go down 1, 2, 3 over 1. So down 3, -3 over 1. But when you divide by 1, -3 divided by 1 is still just -3. So we would only write the -3 because dividing by 1 doesn't affect the number itself. If it's 1 over something, like if it had been 1/2, you must leave the fraction for it to be correct. Now something that can also really help with any of the graphing sections is a graphing calculator. If you don't own a graphing calculator like a Casio or a TI, there's also an online calculator that you're allowed to use in the class and you can use on the final called Desmos.com. So Desmos looks like this. When you first go to the website, it'll ask you to launch the calculator. And then the keypad may not be showing. So once we have all this up, we can type in equations and it can graph it for us so we can check our work. So y equals -3. Our absolute value bars are here. X, I believe it was -2, -1. So we can check the equation we wrote with the equation given to us and the picture given to us to make sure they match up. So Desmos is a good tool that can help us find and check our work for all our graphing type problems. And that concludes our video on families of functions.